Welcome to your favourite podcast.
Hello and welcome back to the Copper Connection podcast, the show where we unpack the science and engineering that keeps buildings alive and breathing. I'm your host Chris Bailey, and today we're diving into material science. Now, don't worry, I'm not about to throw you into a chemistry lab. What we're talking about is practical, why we use certain materials in building services engineering, or BSc as we call it, and how these choices affect safety, performance, and even sustainability. If you have ever wondered why plumbers favour copper over plastic, or why fire-resistant cable supports matter in an emergency, this episode is for you. So, let's jump in. So first, why materials matter in BSc. Think about the building. It's not just bricks and mortar, but a hidden network of systems which consists of heating, cooling, plumbing, electrics, and ventilation. Each relies on materials that can handle a very specific job. Wrong pipe material, you risk corrosion and contamination of the drinking water. Wrong insulation, it could overheat, cables fail, lights go out. Untreated timber in damp areas, rot sets in and compromise the safety of the building. Material science is what prevents those failures. It's not abstract theory, it's the reason our designs work, last, and justify the investment. So now let's take a look at the types of materials in construction and BSc. So we have metals, ferrous versus non-ferrous metals. Ferrous metals contain iron. Steel is the obvious one. Strong, affordable, everywhere. But it rusts without protection. That's why we galvanise or coat it. Non-ferrous metals consist of copper, aluminium and lead. They resist corrosion much better. Copper is king in BSc, water and heat and pipework, because it doesn't contaminate the supplies. Aluminium is light and easy to form, perfect for ductwork and HVAC casings. Then we have our alloys and solders. Pure metals are rarely enough. Mix them and you improve the performance. So iron plus carbon gives us steel. Add tungsten and you've now got tool steel, tough enough for drills. Then our solder, usually use tin and lead, which joins metal pipes and electrical components. We have plastics, two broad groups. We have thermoset. Once hardened, they stay rigid, like epoxies in anchor bolts are a classic example of this. Thermoplastics often soften with heat, solidifying on cooling. Think guttering, downpipes, cable insulation. And there's also XLPE, which is cross-linked polyethylene. It doesn't melt, it heats and stress resistant, and you will see it in underfloor heating, hot water pipes and high voltage cables. Then we have our ceramics and fire clays. Ceramics gives us sanitary air like toilets and cisterns and basins, as well as electrical insulators. Fire clays resist extreme heat, so they line fireplaces and furnaces alike. Then we have our rubbers and sealants. Synthetic rubbers are everywhere in BSc. Hoses, gaskets, expansion joints, and silicone sealants deserve a mention. Waterproof, flexible, and long-lasting for joints and glazing if protected correctly. So when engineers are choosing materials, it's all about behaviour. So we have tensile strength, pulling forces, so cables, wire ropes. We have compressive strength, squashes under forces. So we can use this in our concrete foundations. Conductivity. Copper excels at both electrical and thermal transfer. We have malleability and ductility. shaping steel sheets, stretching copper wires. Density, weights affect handling and structural loads. Hardness, wear resistant in floor finishes or bearings. Toughness, withstanding sudden shock. So a lot of our plant housing and pump castings are tested through toughness. Thermal expansion, copper pipes expand when heated. This is why installers leave expansion joints or U-bend in long runs. Degradation and failure. Even the best materials break down at some point. For example, moisture freezes inside bricks, which over time will split the faces. Untreated timber absorbs water, so over time fungi will grow and then that'll increase into rot follows. UV lights fade and crack plastics. Fatigue from constant motion, so fans, pumps, joints, leads to cracking at some point. So engineers counter this with coatings, treatments, inspections and sacrificial parts designed to fail safely. Then we need to look at corrosion and the environmental effects on our materials. Corrosion is simply materials reacting with their environment. So oxidization, aluminium protects itself, but iron rusts until there is nothing left. Galvanic corrosion, copper joined to steel in water, forms a circuit. One corrodes faster unless we use isolating joints. Erosion corrosion, grit is fast flowing water, so pipes, elbows and pumps inlets. Atmospheric corrosion, acid rain, salty sea air, individual and industrial pollutions all accelerate attacks. UV and heat, plastics soften, warp or even crack if they're not stabilised. Engineers use the Electromove series to predict when materials will corrode when they are paired together. Then we have our fire and thermal performance. Not all materials behave the same in fire. So we need to look at combustibility. So PVC burns, mineral wools don't. Fire resistance, ceramics and fireclays hold their form at extreme heats. We need to understand the melting points of our materials. PVC installations fail quickly, where XLPE lasts longer, vital for emergency circuits. Containment, if there is a fire, we need to contain it for long enough to let people escape. So we need to use fire collars, insulation and dampers that stops flame and smoke, moves in between rooms with ease. And everything we do, we've got to think sustainability. Performance is one thing, environmental impact is another. Copper, endlessly recyclable with no loss of quality. Steel is energy hungry to produce, but the most recycled building material worldwide. Concrete is carbon intense, but greener with GGBS or fly ash mixes. Plastics degrade with each recycled cycle. So designers aim to reduce volumes or use greener polymers. So everything we do will always be scrutinised through standards and testing. How do we trust what materials can do? Well, that's the testing and standards. So we have to test for tensile strength to confirm the strength of material. We have to do hardness tests where Brinell, Rockwell, Vickers, impact test like Chirpy measures brittleness, fire tests that are up to British Standard 476 or even European Standard 13501, classified combustibility and flame spread of a material. Labelling is also important. It matters. If you see BSEN 105 copper tube, you know it's certified for drinking water. So, what's the bigger picture? Material science underpins every BSE decision. The right material means safer drinking water, reliable heat and cooling, electrical systems that don't fail, and fire safety in an emergency. Lower carbon sustainability buildings. Next time you step into a building, remember every hidden pipe, cable and duct was chosen for a reason. So that's it for today's episode of the Copper Connection podcast. I'm Chris Bailey, and I hope this gave you a solid grounding in how material science shapes our industry. Join me next time as we explore another essential topic in building services engineering. And remember, the right material in the right place makes all the difference.
We'll be back next week. In the meantime, please subscribe and thanks for listening.